Hello everyone. In this segment, we are going to see delete operation from linked list. All right. So a delete operation in linked list means given a list and given a index. Okay. So you have a list and as a parameter you want to give the index and means index or position, or you want to delete that value from that position. So we know that, just a recap about linked list, when we first initialize a list, so all we have the head node pointer, okay, means the head pointer that will point to the first node of the list, but the first node of the list will not store any value of the list, okay. So the first node will be actually the next pointer of the head node, okay. So the first node, I mean the first value of the list will be pointed by the head node, okay, will be pointed by the head node of the list, okay. So this is our initialization. So and then each list looks like this, and the way we do the traversing, we use two node pointer, previous node pointer and current node pointer. So in each iteration we'll always the current node pointer will always point to the current node that we are visiting, and previous node pointer will point to the previous node of the current node, okay. Now when we are going to implement a delete, okay, how actually we are going to do that? So let's say this is our list, head pointer is pointing to the uh, head node, we can say that it's the head node, okay, and the list value we are going to store from the this node, second node. Let's see, we have 40, this 4 node, okay, and it's pointing now. So given a position, we want to, given an index, we want to delete a particular item, particular node. So if the index is 2, that means it will start from 0, 1, 2. So we want to delete this node, okay. Now what does delete means? So, and how we're going to delete a node, okay. So if this node doesn't exist, how our linked list is going to look like? So 10 should point to 20, and 20 should now point, instead of 30 it should point 40, right? So if we delete node 30, that means 20 should point node 40, okay. So all we have to do, we have to take care of this pointer. This pointer means the pointer that of the node 20, okay. So instead of pointing 30, it should point to 40, okay. All right, how I can do that? All right, what I will do, so I have 40, I have null here. So at the same way, we're going to use current and previous node pointer, and this is our head pointer. So previous will start from here and current will start from here, okay. And we're going to run a loop starting with I equals to 0, and we're going to keep continue this loop until I equals to index, okay. So when we'll reach at that position, when I equals to index, let's see, I equals to index means index equals to our 2, okay. So at that position our current will be pointing to this node 30, that's what we want, okay. We'll stop at this point when current is pointing to node 30, means this is the node that we are going to delete. So and at that point our previous will point to node 20, okay. So what we can do, okay, so we need this node 40 because now 20 is going to point 40. And how we can do that? We can use the function current get next, right? So get next function of current is going to give the address of this node, okay, address of this node. All right. And now, instead of pointing to the node 30, previous is pointing to the node 30. Instead of that, previous is going to point to the node 40, which is current of which is get next of current. Now that means we have to set next of previous with this node. Okay, so this is our get next, which is 40. Okay, and now previous is 20. Previous of set next, we are going to point to the node 40. Now instead of pointing to 30, after this line, this is going to point to node 40. Now let's start from head pointer. We can see that we have the value 10, 20, 40. Okay, so as we are losing this address, we will not have any access to the node 30. But that is not actually going to delete the memory allocation for this node. I mean, you can see that this node is still there, right? So this node is still there. It is pointing, it is being pointed by current pointer. All right. So right now this is not part of the list, but this node is still there. What we can do, just we can write another line of code. After this line, we can just line another line of code like delete current. Okay, and this will be actually at the end of this line. That means we are going to delete current. And you know what does delete operator, what does delete operator do? A delete operator will deallocate the memory allocation, okay, that the current pointer is pointing. So current is pointing to this node. This memory allocation will be freed from the memory space. Okay, so this will physically deallocate this memory space. All right, so that's actually what we are going to do. So the node that we want to delete, okay, we'll reach at that point, but we need also the address of the previous node. Okay, because now the previous node will point to the next of the current node. Okay, so we'll change this next pointer address. So now it will not be a part of the list, you can see, right? It will not be a part of the list. All right, and then we can just delete the memory allocation directly. All right, so let's see how it will look like. So let's see, we have this value in our list and we want to delete index with index 2. Okay, so we're going to maintain this current node pointer that will be actually pointing to the first node value, first value of our list. Okay, and previous will start from the same as the head pointer is pointing. Okay, so we want to delete at index 2, so that is our 0, 1, 2. So we'll stop when current is pointing to the index 2. Okay, so you can see current is now pointing to the index 2, which is 30. Okay, that's what we want to delete. Okay, now we are going to set the next pointer of the previous pointer with the we're going to set the next pointer of the previous pointer with the next pointer of the current pointer. Okay, let me say that again. We're going to set the next pointer of the previous node, okay, with the next pointer of the current node. Okay, so and then we can just delete this node by writing a command, by writing a line like delete current. Okay, so let's look at this code here. Okay, so when we reach at the index equals to delete index, we are going to we are going to actually, the next pointer is the current get next, means it's the, this is our current, so this will be our previous, Okay, and this is our next of current. Okay, so next pointer we are using to point to this node. Okay, so you can just break it from here, and then using the previous use the previous to set next with the next pointer. All right, so we didn't write this line here, just make sure that you delete the memory allocation that is pointed by, that is being pointed by current. Otherwise what will happen, this current node will be, this node will be a part of the list. Okay, this will be deleted from the list, but the memory allocation with the current node will be still there. So you can actually write another additional line like delete current. Okay, all right, we actually saw most of the operations. So just one more operation we had previously, but I guess we didn't talk about that. Like, how do we check whether the list is empty or not? We know that when we just create a empty list, that means we just have a head pointer. All right, just one node, and the next is null. Okay, so this means it's a empty list. Okay, so how do we check whether the list is empty or not? So we can check whether the list is empty or not by checking the next pointer of the head node. Okay, head node means the node that is pointed by the head pointer. So head pointer get next equals to null. If it is true, then we say that the list is empty. Okay, but if it's not null, means we have at least one value in our list. So these are the all of the operation. We can actually we can insert a item in the list, linked list. We can insert a item at the end of the list or at the middle of the list at a given position. We can read or modify a particular value. Given an index, we can read or modify particular value in the list. Okay, so we can check whether a list is empty. We can count the number of items in the list. Okay, by count means actually we have to traverse the whole list. Okay, until we find our current is pointing to the null value. So when current will point to the null pointer, that means we are done with traversing the list. We are going to just keep track of a current variable. Okay, we're going to just keep track of the another variable which will count the number of elements in the list. So let's compare array versus singly linked list. Okay, we'll talk about doubly item linked list later, and that will be actually our part of homework. All right, so reading or modifying a particular item from array versus singly linked list. So if we have a index, in that case in array, it's actually very efficient. We need just it's just a one operation. We can read or modify a particular item. Given an index, you can read or modify an item from the array with order of one runtime. Okay, but in singly linked list, actually singly linked list, we have to start from the head pointer. Okay, we have to start from the head pointer, then we have to traverse the list, and in worst case we may have to traverse the whole list. Okay, if we want to read or modify the last item in the linked list, we have to traverse the whole list from the linked list. So in the worst case, runtime will be order of n. So insertion, we saw that in array it's order of n, singly linked list also order of n, because we have to traverse the list. Okay, and worst case is that if we want to insert at the end of the list. Okay, and the behavior will be order of n. Delete same, array order of n, singly linked list also order of n. Is empty, it's order of 1, order of 1. Okay, so why it is order of 1 in singly linked list? Because I mean, we'll just check whether the next pointer is null or not. Okay, next pointer of head pointer is null. If it is null, then means it is empty. If not, that means it's not empty. Okay, it's an order of 1 operation. So count, it's a order of 1. Okay, all right, we can, I mean, in our implementation we saw that we actually always keep track of one variable. Okay, we always keep track of one variable like end of array, that will give us the index of the last item. so we can know how many items is in our array. But in singly linked list, we always have to actually count the all items in the linked list. Okay, so that's the comparison. You can see that all the operation, actually most of the operation takes order of n runtime. So the main advantages of linked list is that it's very flexible in size. Okay, it's very flexible in size. It doesn't have any fixed size requirement. So whenever you have a element, if you want to add a element in your list, you can just reserve a space for that node, for that value, all right, and you can insert that value in your linked list. You don't have to reserve a maximum size amount. You don't have to reserve any amount of memory space for the maximum size, like we did that in the array. Okay, so now in the next discussion we'll talk about double item linked list. Okay, and that will be a short discussion, because we'll just give you the idea of what a double linked list looks like, and we'll ask you actually to implement that in our homework. Okay.